This is Earth, the place where we live. This is our place in solar system. The entire solar system, with all its planets and stars, can be put to this small yellow square. If we zoom out, we can see that our solar system has interstellar neighbors. And all together they occupy a very small part of our entire Milky Way galaxy. The Milky Way itself is not the only galaxy in the universe. Our galaxy with its neighbors form a local group of galaxies, and they in turn form a supercluster. But even supercluster is not the whole universe. All the stars, planets and the galaxies I have listed are all just small circles in our universe. This all our observable universe. Impressive, right? Now, can you imagine how insignificant we are in the entire universe? How our field of vision is limited when we observe the space? Despite our small size in universe, our scientists making impressive results. The farthest human's journey is made up 13.49 billion miles from Earth. The Voyager 1 was the first man-made object that passed heliosphere. The scientists do not stop at this and continue to discover new planets and galaxies. My team from IREP Research Center is no exception. A team of astrophysics and programmers are developing a software named Piebolt, which helps to observe astronomical objects such as diffuse interstellar clouds. Through this video, I'm going to show you theoretical part of the work in simple explanations and give you overall picture of an event. First, let's get acquainted with astronomical terms such as interstellar clouds, light, electromagnetic radiation, absorption and emission of spectrum. What do we observe? What is interstellar medium and interstellar clouds? The word interstellar itself means between or among the stars. But what do we have in the space between stars and galaxies? Many people think that outer space is empty, but this seemingly empty space between stars isn't really empty. Sure, it's much emptier than anything here on Earth, but nearly 1/6 of our galaxy's mass lives in a space between stars. The stuff between stars is called interstellar medium. ISM is 99% gas and only 1% dust. Most abundant element in a gas is hydrogen. It makes about 3/4 of that gas. A quarter is helium. Only a couple percent of gas is other elements such as carbon, oxygen, magnesium, iron and uranium. The ISM is not a new form, it's found in two main forms. Dense and cold regions of ISM is called interstellar clouds. Depending on density, size and temperature, molecular dense and colder interstellar clouds is called molecular clouds. Ionized and more warm clouds is called diffuse clouds. The second form of ISM is hotter and more dilute regions. So that's all about interstellar clouds. And if you remember, I have mentioned that in our project we observe astronomical objects such as interstellar clouds. So now you know what we observe. The second question is, how do we observe that astronomical objects? Our only contact with distant objects is their light that journeyed across the universe to reach us. Nearly all information we have about universe comes in the form of light. So let's answer to the question what is light and what it can tell us about astronomical objects. Light is a wave and flow of extremely small particles at the same time. Elementary particle of a light is called photon. Light can be created by making an electron oscillate. This creates an oscillating magnetic field and oscillating electric field. That's why we call light electromagnetic radiation. Light can act as a wave and have same properties. It has wavelengths, frequency and speed. Different colors of optical light have a different wavelengths, and so does the rest of electromagnetic spectrum. When light interacts with matter, it produces spectrum. There are three different types of spectrum. According to the Kirchhoff's law, the excited atoms within a hot dense object give off light of all colors or wavelengths and produce continuous spectrum. For example, due to the high temperature of star's interior, it gives continuous spectrum. The second type, when the light from continuous source passes through the cooler and dense regions of ISM, certain wavelengths of light are absorbed by gases. In this way, we get absorption spectrum. The third, emission spectrum, is produced when the excited atoms within a hot cloud of gas give off only particular color of light in a black background. As in our work we are dealing with absorption spectrum, let's have a look for a reason of black lines on a continuous spectrum. As I mentioned before, the light is not only wave, it's also flow of extremely small particles which carry energy. And when the light interacts with gas cloud, the photon gives its energy to the nuclei of an element. If photon has right amount of energy to change the energy level of electron in an atom, this photon will be absorbed. Let's look at example. When electrons absorb photons' energy, they transition from lower to higher energy levels. Electron transition from n is equal to 2 to upwards absorb energies that correspond to the frequency or wavelengths of visible light. For example, when an electron transitions from n is equal to 2 to n is equal to 3, the energy absorbed is correspond to the wavelengths or frequency of red light. And when electron transitions from n is equal to 2 to 6, the energy absorbed corresponds to the violet light. One more important thing is that the electron which was moved to higher level cannot stay there for a long time and it drops back to the origin. This all means that gaseous elements in the interstellar clouds is sensitive to only certain wavelengths of light. When we first receive an absorption spectrum from telescope, we can list all its constituent elements. So encoding of light is key to understanding what the universe is made of.